I will be picking up a little bit from where we stopped in the middle of the notebook to cover the pipeline and the code sample that we were going over. And that would be sort of the first part where data modeling, training and optimization and evaluation, those pieces were remaining. So I'll go over the code. And then I'll introduce neural networks a little bit. And I'll have, so there are some very good readings for neural networks to understand them from like step one, which are good tutorials. I'll add links to all those, and you can go over those in detail after the class. And there's one more component I want to discuss today is around projects, because now I think the enrollment has almost settled. Like everyone who's enrolled is gonna stay in the class, so you can make teams and not be really afraid of someone leaving the class. And I'll give an idea of what initially I discussed, how the project structure would look like. And now that you know the process pipeline, it might be more likely that you can think directly in those terms. So just to review before going in, okay, reviewing the process. We first gathered the data. So the process is clear, and in terms of the problem that we worked on with the toxic comments, there was a process where we were collecting the data. It was in the form of a CSV, and we gathered it, and we sort of split it apart into different blocks and dealt with it. Then there was the extracting features pipeline, right, where we converted that text data into 422 sized vectors, where each basically, which were the count vectorizer, where your sentence, which was a comment, was broken. A comment was ultimately represented as a long vector. So I'll go over that part again, but then the next steps were developing the model, which machine learning model you want to use on that derived structure, how to train that, how to optimize the training process, and how to evaluate. Okay, so and in the middle of the training process, one thing which is this iteration cycle is important is that whichever algorithm we are choosing, if it's an iterative algorithm, has to go through this process that we will send the data into it, create predictions from the algorithm, from the model, derive a loss, send the loss back to update the model, and at each iteration we continue the same process, right? And leading up to sort of creation of the validation data. Validation data at each step is the point that we are using to verify what we have done is correct or not. And then once the model is, has gone through this iteration, it's a trained model, and then we evaluate. Okay, so I'll move back to the same problem that we were working on. Okay, before I describe model definition, were there any particular questions in how we reached up to this stage? Okay. Okay, so before developing the model, we have the data in the form of input to the model being a long vector of 422 elements. So its shape is 422, and the output are 6 different classes, right? So we have 422 inputs going in, 6 outputs coming out, and these are the kind of, this is the requirement, and then we need to develop models for it. And this small portion, I mean, let me know if there's any question around it. This was basically converting the data into training, validation, and test. We are splitting the data into 3 portions, right? Up till this, everything is clear?
And what, for training, validation, and testing, what percentages of the data?
So since this is 100, everything is, yes, it's 60, 20, 20, because we are just working with 100 samples. So the percentage is same.
Can you say something about the difference between validation and test?
Yeah, so remember the cycle that I was showing, the iteration cycle? Validation data is something that I'm using at each iteration to see how my model is being trained. So I'm not stopping the training process. I'm validating at each step of the process and seeing what are the results on my validation data. But once I have gone through a certain number of iterations that I feel are good enough, then the data that I evaluate on is the test data. So validation is like
this. Validation is being used to train the hyperparameters.
Yeah. ideally, where like number of iterations is one of the hyperparameters. Like how many steps.
In a public test for which you're going to compete against other people, they would typically give you training and validation and not give you testing. Is that correct?
Yes, when you're in the competition
When
phase.
you're in a competition,
Yeah, they
you
won't
would
even
get
give
some
you
validation.
Yeah, they won't even give you validation. You will generally they'll just give you training and you create a
Split it
part.
how you want to.
Yeah,
Right, okay,
you
okay.
create a
That's
test.
what I'm asking. I think the validation is somehow part of the training.
Yeah.
So somehow, right? I'm splitting it to two
Exactly.
hyperparameters.
But test in a real case scenario, you don't know the labels on the test set. You just submit those and then maybe someone else knows and they give you the result. In our case, we know them, but we treat as if we don't know and just evaluate in the end. Right? Okay. So for developing model, this is going to be a run through, first of all, with the model as well as using a normal library, Keras, inside TensorFlow. So we are essentially using TensorFlow in a package, not a package, a library inside TensorFlow is Keras. So I'll sort of explain how Keras happened and what it is, but what I'm going to go over are two very basic kinds of models. So let me first explain this version. So TensorFlow is a large framework, which is at present sort of the best deep learning framework, which provides you the ability to build very large neural networks, which can be trained on top of simple CPUs. If you just have CPU hardware, you will use those resources to train and evaluate on those models. If you have GPUs, then also your code doesn't change. Basically, it's the underlying framework of TensorFlow which will take care of optimizing the performance using GPUs. And similarly, the third level is TPUs, tensor processing units. So TensorFlow is optimized even for TPUs. That's one difference between PyTorch. PyTorch at the current stage is GPU. So there is some work going on. So in the nightly version, they have TPU support, but mostly it's only up to GPU. The TPUs are tensor processing units, which are something that like Google created those, and they are available only on Google Cloud, I think. I haven't seen anything besides that, but they are dedicated to deep learning. They are built in a way that is even better than GPUs. The optimization is even better than GPUs, and they're massive. So the Google Cloud, the ML inside Google Cloud is powered by TPUs. So if we want to use a TPU resource, we can actually use that using the Google Cloud. But TensorFlow is the framework on top of all this. It provides you several, so it's a big library which provides you all the tools you need to build neural networks of any level. You can perform research, like if you just want to use them as an end user, everything is there and you just want to deploy a model. Or if you want to build if you have an algorithm, which is, let's say you're building your own neural network layers and you want to write an algorithm, you can do that. So any depth from research to production, you can use TensorFlow for all those. So Keras is a library. It started as a machine learning framework, which was more user-friendly, which was easy to use if you're particularly a Python programmer. It's written in a very Pythonic way. And if you don't want to go into deep details of how the algorithm is doing things, and you just want to use it as a layered architecture, Keras was sort of the best user-friendly library. And it could work on different backends. It would run on top of TensorFlow. So you install TensorFlow and you install Keras, but you write your code using Keras. And then there used to be another library called Theano, which was developed by Mila, like the research lab at Montreal. And it would just basically, you can switch the backend and use Keras on top of it. Then Keras got merged into TensorFlow. The creator of Keras, Francois Chollet, also is a part of Google now. He's in Google Brain. So at some point, I mean, everything inside Keras has been integrated into TensorFlow. And while Keras continues to grow as an open source project, you can say that if Keras is at 3.5.2 version, TensorFlow is implementing 3.5.0, or like it's slightly behind the Keras state, but inside TensorFlow, it's more stable. It has access to all the other resources of TensorFlow, which means TensorFlow has very good APIs for using datasets, for reading directly from data in an optimized way. If you have really large datasets, how do you use that? It has some work on deploying models into distributed environments. and deploying. There's an idea called TensorFlow Lite, which will be helpful later on to applications of the scale that we will focus on. But TensorFlow Lite means that even if your neural network model is really heavy, requires a lot of compute, TensorFlow Lite has a way of converting them into smaller models, which can go on your edge devices or mobile phones. So Android phones use TensorFlow Lite. Similarly, there's TensorFlow.js, which is client side, which is basically running TensorFlow code on the web browser using JavaScript or on a Node.js server. But the idea is that now there is this part of code which is written in JavaScript instead of Python. But because of TensorFlow.js, they have written it in such a way that a model trained using this framework, let's say it's a Keras model trained using TensorFlow. Once you save that model, your TensorFlow.js code can use it. So you use really powerful machines to train a model, and then when you're deploying your model on the cloud, it can actually run on the web page itself. It doesn't have to run on a server again. So these are sort of advantages of using TensorFlow. Now, the way they have included Keras inside TensorFlow is that entire package, almost like I would say 95% of the capabilities of Keras are now a part of TensorFlow. So tf.keras, like TensorFlow.keras, is basically Keras. And going into the course, since we are not building algorithms, I prefer to use Keras. It's very easy to understand, it's very intuitive. And there's also a nice visualization tool which helps, I'll show you the visualization, but to sort of see how a model looks like. And that's the way I'll go over neural nets today. Like I'll build different models just to give an idea that if this is the input and that's the output you need, how does the model, how do you build this layered architecture? Okay, so going into it, you just import TensorFlow as TF. From TensorFlow, you import Keras. Keras is your library that you'll be using. Now, our data was long vectors, and our output is we need sort of six individual predictions, right, for multi-label classification, right? So, did anyone cover some of the readings on machine learning crash course, or scikit-learn? Okay. So my explanation of logistic regression in a very small set is, let's go over the slide. Yeah, so this is linear regression. Y is equal to Wx plus B. There are parameters which are W and B. B is a bias, but W is the primary parameter that you want to learn, the set of weights. And given an input, you learn Y is equal to Wx plus B, right? You do this dot product and you have a result. Y is your result. And you train your model for that. But that's linear regression, which means your value is a floating point number. You do logistic regression, which means on top of that value, you are doing a sigmoid. What is a sigmoid? It's basically a function which looks like this. So if you're doing some, maybe not. I mean, this should be 0.5. It's always between 0 and 1, right? The step function in math means this, right? If you're under 0, you're 0, and then you go 1. This is a smooth step function that you're transitioning from 0 to 1, never really reaching the extremes, but I mean, reaching extremes at infinity. And it's defined by 1 upon 1 plus e to the power minus 6. So this is a logistic sigmoid function. When you have a regression value, which is your x, and you apply this function to the value, your result is going to be somewhere along this. It's going to be a value between 0 to 1, right? So now, no matter what was your input, and no matter what was y from linear regression, when you apply this logistic sigmoid operation on top of it, the result is within 0 to 1. And that's what you use. That's what you use for classification. That's what you use to define sort of the probability of something. But your result has been limited to a space of 0 to 1. That's the very basic architecture of logistic regression. given an input vector x, you want to learn weights w by determining the result, which is y is equal to logistic sigmoid of wx plus b. Okay. Up to that, that's logistic regression. And neural networks can be seen as an extension of this, which I'll discuss later on after showing you logistic regression. But up to this point, is it clear to continue?
So after you have the logistic regression, you have like 0.9, that's between 0 and 1. Does that then translate to 90% confidence score?
If that's interpretation is dependent on the problem.
Okay.
So if you want to
it's
interpret it,
classification.
yes. If it's classification and you are saying, yes, I want a classification score from 0 to 1, and you sort of, let's say, treat anything beyond 0.5 on the sigmoid means 1, then it means 1. But the interpretation is dependent on the problem. But the idea of doing the 0 to 1 thing is that you have this standard probability space, right, which is the result space in 0 to 1. Your result, no matter what condition was, is actually now within 0 to 1. Okay. So now to build a logistic regression model in Keras, what we do is, given a certain size of features, which is the shape of x in my wx plus b, you know, how many elements are in this x vector, that's your feature size, and number of classes is the output that you need. How many outputs do I need? So now, this isn't the very typical logistic regression that I explained, right? That was y is equal to wx plus b, where you assume that y is a single, like it's a floating point number now, between 0 to 1. But since we have n classes, and n classes can be greater than 1, we are in a way doing n classes number of logistic regressions. So in this case, we have 6 logistic regressions. And when you're building a model, you can do all of them together. But I could have had separate 6 logistic regressions, and each of those would sort of do the same thing that this bigger model is doing. Now, how do we define this is,
They don't interact with each other in the bigger model.
Yeah.
They're essentially
because
right?
yeah, they're not interacting. Because of the architecture that this is just 2 level. And once we take one step beyond, we are sort of interacting. But how we define it is, we have an end, yeah?
Do you mind going back just for a second? That's where you are. Okay. Did the multi-layer perceptron come from a logistic regression? Because it's similar but not quite. Because it seems like the wx plus b is taking the place of the x, and then the sigma or whatever like went through. But how come it's w prime and then like the sigma thing, but not b prime and sigma? Do you see what I'm saying?
It is B
Because
prime.
It is B prime.
It is B prime on the end. It's just.
I know,
it's
but
just
why
a-
isn't it? See, you have the w prime and then the sigma thing, because the wx plus b is kind of taking the place of the x in the logistic regression, right? And then the w prime, because you're like one step down, and b prime because you're one step down. How come the sigma permutated through to the w?
Oh, you're saying it's not sigma prime or something?
Yeah, it
No, no, no.
should be b prime sigma. Like, do you see what I'm saying? Yeah, you see
Sigma
what
is a learning rate, I guess. So that has-
No.
That is same across all the matrices.
Sigma is not the learning rate, first of all, so don't start on the confusion. Sigma is the logistic sigmoid operation,
Okay.
right? That's a function. So this function was applied to wx plus for input x when we were creating this. We had wx plus b and sigma on top of that,
Right.
right? Now let's say, I mean, I could have written this to be y prime and y over here, but what I'm saying is that when you go layer after layer, your result from previous layer is what you're using
As your x.
as your x.
Right.
So that's your x.
Right.
But now you're treating new weights, new biases for that particular layer, because it's a different layer.
Right.
So this layer has w prime, b prime, or maybe w1
No,
will
I'm
be.
fine with that, but what I wasn't fine with is why you have the 2 sigmas and multi-layer perception. Like, I understand like if you took a logistic regression and substituted out the w with w prime or b with b prime and the x with wx plus b. All of that makes sense to me. But why there's that extra sigma between the W prime and the WX plus B, I don't understand that one right there.
Because you want to use the sigma result. You don't want to use the linear regression result.
Oh, wait, so it's the I see what you're saying. Okay,
I mean,
sorry. That makes
explain
sense.
the dynamic
No, 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 I'm
regression.
good, I'm good. So this went in here. Okay, yeah, no, sorry, I'm good now. Really sorry. Yeah, I wasn't taking this together.
Okay, so now looking at the model, we have an input layer, which is taking in all the features, right? So it's taking in a vector of a certain size. There are two kinds of APIs inside Keras. One is called functional, one is called sequential. The way this code is written is functional. What functional means is that instead of having this set of things through which everything will go through, I'm transmitting a value through things one after another, like the functional programming approach of Curry, right? I think that's the term. But just to understand, INP is my input, which says it's an input layer of a certain size, right? Now, whatever is the value that I get at the input, a dense layer is responsible for doing WX plus B. So the particular part of linear regression, which is WX plus B, is being done when I use something called a dense layer. So the scale.dense, scale is just a way to say keras.layers in an easy way, right? So the dense layer is doing the WX plus B part. And if you add this factor that there's an activation on top of it, then it's also doing the sigmoid. So now, sticking to sigmoid only because it's logistic regression, we are saying that we want n classes number of outputs. So that is the number of logistic regressions we'll be doing, because this input will have so many W's, W1, W2, W3 till W6 for to be learned, which will be created by this n classes. That's the number of outputs you want to derive. And each of these is basically a sigmoid over WX plus B. So giving the dense layer, that's what you get. But what is the input to this function? What is the input to this layer? It's INP, which was the input layer. So now you have created this two-level architecture. And if we build this model, this is what it looks like. There's an input layer, which has a shape. So none means the batch size. When you will send data through it, what will be the size of data? If it's none, it doesn't care about. There's a fixed size is not required. It will infer at the time of usage. But this shape is known that you have an input vector of 422, right? And since it's an input layer, there's no weight associated, no parameter that you want to learn. And then you have 6 outputs that you want to learn. So you have corresponding parameters, right? And the way this model looks like visually is this. You're deriving 6 outputs. That's what you need, 6 probabilities for each and every label with an input of 422. Just single layer. That's the very basic logistic regression model, right?
I understand the dense. I don't get the input layer. It's just a no-op. It's just putting it in the format of layers. Is that correct?
Exactly.
Okay.
That's why it has no parameters. It's just
Oh, I see. Okay. There's nothing. Okay.
Wait, and Raptor, just to refresh my memory, probably, when you're like, where none is, it's the number of lines, because it was 422 words, unique words, right, that weren't on our stop list. So that's why we had a vector that was 422.
Yeah.
And so none, if you had like 10 there, it would just be 10 lines of 422.
yes.
Is that what the number?
Yes.
But none means it could be 50 million or it could be 10.
How it happens is that when you train the model, you are sending values in a batch. You're not sending one after. I mean, you can send one after other, but you're wasting resources. So you want to do as many as you can, depending on your hardware. So you and that thing is called batch size. Generally, like batches of 32, 64, and whatever is possible is tried. And none means you can use any of these. And this none would actually continue to be the same throughout, because whatever you send as the input, those many outputs would be derived at one step. So this is developing a very basic model, which is a logistic regression model, we know that we had an input vector and we can just do this. And since our result was already in a 0 to 1, 0 or 1 for label, our result is actually going to be, so we can confirm our result. It's a sigmoid, it would be between 0 to 1, right?
And where you have dense 7, params.
Why is it 7 instead of 1 or something?
I'm sorry.
Like dense 7, like why 7? Or
No. Oh, yeah, I guess so. And because I was wondering why the param of the input layer is 0, but at the dense 7 was 2538. Where's that?
those parameters are what you're going to learn.
Okay.
At an input layer, it's x. There is nothing I need to learn. And given an x, I represent it in a certain way.
Right.
But the dense layer is doing wx plus b, so it has to learn the w and the b, right? So there are the parameters. Any other questions around the basic logistic regression model? Okay, so now moving on to neural networks in a way is the multi-layer perceptron. So neural networks have sort of this architecture. You have inputs, right? And then they can go on interacting with multiple number of layers to derive the final output. So in this case, we have one output. So it derives one output. But we had a large number of inputs, and then we had sort of multiple hidden layers. What it means is that a logistic regression was doing, let's say, just this much, right? This final step. It was doing a small piece of, it was training one set of weights and just learning on top of those. But that's good for certain level of complexity. But when the complexity starts to increase, you need maybe more relations between whatever happens. So given my inputs, I can draw a relation. Okay, if I say this much weight on certain word, and among those 422 words, you can learn, okay, if this word appears, I have a certain weight on this word, right? And so on and so forth. For each word, you will learn a certain weight, and that corresponds to one of the labels. But now, what about the relations between those words? What about the crosses that happen, that these two words appear together to really make the situation of a certain kind? These three words appear together, and then only it's a hateful comment. Only if these three words appear together, or four words appear together. Like, you have more relations which are not easy to learn just by assigning weights to the individual levels. You want to go a level deeper, or maybe multiple levels deeper, in order to learn whatever those relations are. One way is to manually define relations. Like in NLP, there is a concept of n-grams, which is like bigrams, trigrams, where what we did, we split apart the words by spaces. So we were just treating one word at a time, right? But we could have also done two words at a time, like pairs of words that appear together in a sentence. So like in a sentence. So in a would be a bigram. In a sentence would be a trigram. So you can start taking more combination of words and putting them as features as well. That's one way of doing it yourself. Another way is you have enough data, let's say, and you want your model to learn whatever combination is best. So you start increasing the number of layers, because now they can learn complex relationships. And that's the idea where multi-layer perceptron or neural networks come in, that you can now start to learn really complex relationships by combining a large number of small relationships. So what will happen is that your input data will pass through one layer through weights, and will sort of convert itself into a new vector of a different size. But that vector is now more representative of a new state of the data. It's just, I had data which was defined by me manually in certain number of features, but maybe I can learn a large number of features from those, and now I want to perform a learning operation on those. And going deeper and deeper, you build your layered architecture of neural networks, right? So you have a certain kind of input, you learn a new representation on those inputs by learning from one set of weights. You take those representations, you apply another operation on them and learn a new set of weights and new representations up to the point that might be best for your results. So how you decide the number of layers, you can sort of easily decide a minimum depending on the complexity of your problem. I mean, as I said, like if you want more relations between 2 words, more relations between 3 words, a normal logistic regression will just reach its limitations. But there's no cap that you can easily infer. So that's more of a process where you do hyperparameter tuning, which means you keep on trying different things, you build different variants of your model, see whether they were able to learn. Because what will happen is that if you just keep increasing the number of layers, you will have so many parameters that your data will just not be able to learn. I mean, the data won't be enough to tune them up. You won't be able to learn those parameters because there are just so many. I mean, you just increase the number of unknown variables to such a large number that there was not enough data to give any reasonable value for them. So in the process of learning, building a model, you have to find out this somewhat reasonable space, which always ends up resulting in a good model. And it's not that hard of a process. I mean, you can start off with smaller layers and going up and up. You usually reach to a good enough solution easily. And if not, you can create an automated process to do hyperparameter tuning.
So I have a couple of questions.
Mhm.
So one, you had earlier 422 inputs or something like that and 6 outputs.
Mhm.
So we expect the number of parameters to be 422 times 6.
Plus 422.
Oh, because you have an extra.
Yeah.
Right, yeah, okay, fine. And then the next question that I have is the sigmoid nonlinear operation is the key to why we need all these layers. Is that correct? Like if I remove that and just treat it as linear,
Then it's just,
then it just all collapses into a single matrix,
Exactly.
right? There's no, so the nonlinear operation is what's making the layered operation have some meaning. So since the sigmoid operation seems to be key to the whole thing, so do people mess around with different nonlinear functions
Exactly.
to stick there? Okay, I don't even know what they are, but like it seems like right.
Just so and nonlinearities are one of the reasons why neural nets came back. Like they were famous in early 90s, and then they were not famous for I think 15-16 years completely. And then in 2012 they were actually back. So this used to be one of the most commonly used nonlinearity. The nonlinearity means that you're adding this activation or an affine operation. You know what's an affine operation? So if my data is of certain size, can I apply an operation which is applied sort of individually to each and every element, and I derive same number of outputs. So you had a wx plus b, right, which had a particular shape. When you apply sigmoid on top of it, you're not changing the number of values. You're just changing the value itself, right? There's a transformation which happened from one value to another value. And if you apply that to 10 values, you derive 10 values. So you're going from one space to another space without really changing the number of values. So these activation functions are the key players in neural networks, where you have a way to learn, and then you apply an activation on top of it, because that's the nonlinear function which will help you learn something. If we have enough combinations of correct nonlinear operations, we can build up any kind of function, in a certain way. That's the idea behind this. And I think keeping in with the terminology of where neural nets came from, like from the real brain neural nets, they use the term activation, which is like what is the activation coming in from a neuron. If you look at them just like a graph, these are basically different cells and with directed edges, right? And at every cell, maybe you have a function, but if you look at it like a neural network, these are called neurons, and the value that's coming out of them is called activation. So one nonlinearity that's commonly used is sigmoid, logistic sigmoid. Another one is called tanh. So this was sigmoid, right? Tanh is similar function in the -1 to 1 blocks. It's going more or less like this, which means now my value is between -1 to 1. And it's 1 minus e to the power minus x upon 1 plus that's correct, right? 1 minus e to the power x upon, yeah. So that's tanh. which is another nonlinearity. So these two are the most, these two were the most famous ones. And now when neural nets were sort of revived, there's another operation which is called ReLU, or rectified linear unit, which means max ReLU of x is equal to max of x plus 0. That means up till here, if my input is something, the value remains 0, and then I just follow the 45 degree, like x is equal to y is equal to x. So that's ReLU. This is now an activation function which is nonlinearity, but it doesn't include any exponential. So calculating e to the power x is a larger operation. If your machine is doing multiple e to the power x operations, it's going to be heavy, heavy, heavy. Whereas this is a really lightweight operation. You can do a large number of ReLUs without really putting too much compute load on the machine. So the expandability of a ReLU operation is huge. Also, you don't have limitation in the values. So what happens with really deep models is that all your values are within the 0 to 1 or -1 to 1 block. And then the updates that you're making going into the process become very small. The gradients start diminishing. So I'll try to find a reading around this problem, which is like diminishing, vanishing gradient problem, which means that going deeper into the model, if you're just using normal activation functions, the gradient is not good enough to train the function anymore. Whereas in ReLU, because you have values which are so sparse and so large, your gradient still computes to a really good change. And in the process, you are actually sort of controlling large patterns and making big changes rather than just tweaking around things a little bit in order to learn faster. So, and these are just 3 of the most famous ones. Then there are several variants of ReLU, which are like leaky ReLU, p-ReLU, LU, and many, many, many. So several activation functions can be tried over here. And that's the key to just keep on expanding neural networks. On the final layer, you sort of use an activation which is more similar to the result that you need. Since we needed a value between 0 to 1, we would use a sigmoid. If we, let's say, needed a value between -1 to 1, which is another important use case. Like if you are providing a trust score to someone, you maybe want a value, -1 says I don't trust this person at all, 0 says I'm neutral, 1 says I trust them completely. You want a value between -1 to 1. Then tanh is a better operation, right? So these are activation functions, which I will show how we can use those.
You mentioned something about a reading where we would have seen something about logistic regressions.
Yeah.
Can you point to where that is on the website? So not in readings.
No, in the resources for the lecture.
For the specific lectures.
Yeah.
Okay, got it.
Should I add them in the readings? Like I can make a big list of all the resources.
Right? Like I went to readings and downloaded stuff. I said you readings. I'm like, I don't know anything about it. Okay.
So readings I see as being like assignments, sort of. So like that's what
Readings are more or less assignments.
That's what will have to be. That's what will be prepared to like write about on Piazza, and then resources. But it would be useful to say like what resources are more,
For a particular thing.
or just like.
Well, you're going to eventually give assignments. Like I'm assuming that Python thing you're going through is eventually going to turn into.
Yeah.
Could you guys?
Yeah,
just
with
go
the
write some
neural
code, and if at some point there was links that say,
Yeah.
here's some constrained set of things to read to help you do this.
Like if we had covered the entire process on Thursday, I would have converted that into an assignment. Now I want to go over the model and training part, because without that, it's just feature extraction. Then it will convert into an assignment. And okay, I'll try to like add more directed links as well. But if you don't have a good machine learning background, then I'd really, really recommend going through this. I mean, you don't have to attend all the videos and everything, because total it's 15 hours, but they have split it so nicely that up till the point that you feel is good enough, you can just start to learn it and attend some lectures. They have notebooks throughout the stage. It's done really well. I don't know if there's anything else which is that good. There's one chapter in deep learning book, which I think is good. I mean, if anyone wants to, okay, there's one particular lecture which works really well, but one particular chapter in the deep learning book on ML basics. It sort of covers everything going up to the deep learning point because they want to sort of converge to a basic setup of information. They describe different types, supervised and supervised approaches. It's a good chapter to read. And then scikit-learn and NTKGenSim are the libraries that we used. Okay, coming back to the model. So logistic regression was a model which used an activation called sigmoid, right? The basic activation that we are using.
Sorry.
Okay. And now, if you want to build slightly complex model, we can start building a layered architecture, which is the multi-layer perceptron or the neural network. And can the way I describe this one, can anyone describe this particular model? And then I'll go over it.
So the model has two layers. So the first one has 128 nodes.
Mm-hmm.
The second one has 64 nodes, and they are fully connected. So that means that every single node in the first layer is connected to the one node. For every are the 64 nodes in the second layer. So and here the activation function uses one. Yeah.
So doesn't that have to be a layer to go from 64 to 6? So I feel like there's, I don't know how you count layers. I feel like there's 3, not 2. I don't know how you're supposed to count.
Yeah, so there are 3 layers. So you were right about the 128 and 64 layers. These could have been like variables. I just built a small model. So this model is taking in an input, right? And then passing it through one layer, a dense layer, which is the WX plus B kind of layer. But the number of outputs of that layer is 128. So we are learning this large layer in the middle. We started, not really large when we started with 422. We are sort of reducing the space only, but we are coming down to 128 neurons, which takes the input as X, but now the output of those neurons, right? So now you are transferring to the second function. You are going through one more layer, which is giving 64 results. And that output is going through the final layer, which is giving you the same 6 probability values. Yeah, n classes is the number. So you can see, then I'm giving it a value, basically whatever is the shape of targets. So we have the targets variable. That's the number of classes. Whatever is the shape of features, that's the number of features. This is what we give to the model, but now it's a larger model. And if we,
do you count the input layer as a layer? So like with this would be 4 or 3?
I would call it a 3-layer model. Input layer is more or less to give you the representation. If you use the sequential model, so this is the functional API of Keras. If you use the sequential API, you don't need to have like an input in this way. But I prefer the input layer. Functional API, if you like functional way of programming, first of all, then it's the best API to use. Second reason is that if you want to share weights, if you want to have auxiliary outputs, and like if your model looks really complex, then functional API helps a lot. So I'll leave this diagram over here. We can have a 5-minute break at this point, and then I'll go over the architecture. We'll restart. Just to review the model with multiple layers. Were there any particular questions around how we created this model? How a multi-layer neural network is created? So this kind of function, this approach is pretty much clear now, right? Okay. So now if we talk about the activation function, right? For now, we wrote all of these to be sigmoid. But over here, we can also use tanh. And
Can you use different activation functions?
for different layers, yes, you can. I mean, I can sort of have like a ReLU over here. I don't think that's a good idea, but yes, you can, because now the differentiation that's happening at different points is really weird, but yes, you can technically. So let's say we use different tanages, and even the final output that we want is now a tanage. So now, earlier the final results were always going to be between 0 to 1, whereas now they can be between -1 to 1. So I will show a demo of how to do that. Where I go.
Hold on a second. First off, in the future, when you say something, sometimes if you, like just now you wrote TANH, and I had written TANH, TANAG, because I couldn't understand that you said TANH.
You wrote like 10H?
No, I wrote TANAGE,
TANH.
right?
Okay.
Instead of TANH.
Right.
But the other thing is, the numbers that you got, the 128 to 64,
Mhm.
I know that we wanted 6 as our output, but for the 128 and the 64, did we put those in?
Those
Or did the
are
system generate
no, those are a part of the hyperparameters that I talked about in last class, right? Those are some
Yeah.
choices that you will make.
Right.
While
So
building
we
your
could have
model.
said 230 instead.
Anything.
As our first.
Yeah.
Okay, and then just see what kind of thing. Okay.
Exactly.
perfect.
So when you train enough models, you have sort of, you define your ranges that this will definitely not work. I mean, I have a model which is taking in such a complex data set, and now I say, let's just put it down to like 10 neurons. It's not going to learn that. So you start to develop an understanding,
Okay.
and in the end, within a big set of hyperparameters, you just keep on tuning.
So let me ask that in a different way.
Mhm.
I know nothing about machine learning.
Mhm.
If I get a new data set, how many times do I have to guess? Because as far as I can tell, I randomly guess numbers there and see what happens, right?
Well, you
Right.
So,
like learn an intuition about like what.
well, then my next question is going to be how many times do you have to guess, right? So
Yeah.
how many times do I have to guess? And now, like after I go into it, which we use you as a proxy, then how many guesses do you have, right? So like, because they're two random numbers as far as I can tell.
Yeah.
I can put 20,000. I can put 3. I can put -4. That'll probably crash.
No,
Right? Like, I don't know. I don't know.
The numbers would have to be less than 422,
Yeah.
right? So we know that.
Why it doesn't
Why?
have to be less than 420?
Doesn't it?
Because aren't you trying to get down to 6?
They're
Yeah,
trying to
Why
get
would
down
you
to
go
6
up and
How
because
could you
maybe 422 wasn't enough, and there was so much
how can you
information.
extrapolate
go-
out the data?
You're not extrapolating
further
data.
from 422, because 422 was the number of unique words that were on our stock list. So
Uh-huh.
how could I then end up with a vector that's 800?
Because
422.
Because it's not a linear operation. It's
you did a
non-linear
WX
operation.
plus B where your W was really big.
But you
and-
did say that if you have too many like neurons,
Mhm.
too wide of a,
Then it can't train.
then it won't be able to train it.
Yes, but that's too many. Like in most of the cases, trust me, you will be expanding. And let me give you a diagram.
Will be
Maybe
expanded.
you will be expanding.
That's one example.
Really? No,
Okay.
wait, stop. Okay, I can kind of maybe sort of see that.
No, because you're trusting that it's going to be similar to 784.
Will, you have an input layer, an input layer, an old output layer, and then a new output layer. So your layers, you have 3 layers, right? Because we're not counting the input layer. The hidden layer, it took the 422, and it was like, okay, maybe it's 128 now. And then with those 128, maybe it arranged them in a different kind of way and ended up close to 422 or even 422. I can see that, but I can't see it going over 422 when we only have 422 unique things.
But now we are done with those things. We were done with those things right at the first layer. Yes, we knew some 422 values. They may be the best things that we know at this point, but let's try to learn whether we can get more values out of these. A combination of 2 values, that's more important to me. Let's just create one extra value out of that. So if I'm just doing like 422C2, I've already expanded my space just by saying, okay, maybe the combination of each and every value was giving me a better value. So you exploded your feature space just at one level.
Tell me if I was totally wrong, but I think an intuition for this is I only have a linear operation essentially happening in each layer, right? So if the function I'm trying to calculate is x cubed, I can't get it as a linear combination of one. Like if I have one input x, right? I can't get that. But if I expand that out to 3 intermediate things, and now I can try to do something with it, like now I can go calculate, right? So it depends on the function you're trying to get in the end. You need to go up to represent.
Okay, that makes sense. With
So-
our example.
I don't know if it's right though.
No, but that makes sense. And if it was numbers, I'd be like, yeah, but our example used words. So is that a case where even the other day when we were walking and I said, could one of the things be not just looking at the individual words, but looking at word associations, and that's how our layer could get to be bigger than our original vector? Are you still thinking?
Just as if the video was not being shared. Just
Yeah.
a second.
So I
I
wouldn't,
did
I
that
wouldn't,
so well.
I wouldn't believe what I said too much because he didn't get his chance to say something
Yeah, he wasn't listening. He's busy.
Okay, can you check if the screen is up now? I think it was gone.
Something happened to me. Oh, yeah, it's good.
It's good? You can see the,
Yep.
okay. Yeah, so
Okay, so wait, so James made, I thought, a great explanation. Is that he said, okay, you could start with x, and if you were trying to get x cubed, you couldn't necessarily get it from x in this linear function. So then you end up with like two x's,
Mhm.
and then you could,
Mhm.
right? And I'm like, okay, that's cool with numbers. We have words, right? So with
we
the
had
example-
words at a certain point. Now we're all down to numbers and we want to
No,
learn
but did
relations.
the word, where we stop? Are you doing a different example, or are we still doing the word example?
We're still doing the word example.
So is this a case where, remember we were walking the other day, and it was like, okay, so first you look at individual words, and then you maybe look at words that are near words. Like if I say, you're horrible, I'm saying something bad about you. Or if I say you are not horrible,
Mhm.
I'm saying something not bad about you. So could we then have more than 422 in our vector, because we're also looking at not, we're looking at horrible, and we're looking at not and horrible together.
Yes.
So that's how it could end up being larger.
If you do it manually, that's right. That's the idea of bigrams and n-grams. So not horrible is a bigram.
Okay.
It's two words,
Right.
right? So if you're doing it yourself and providing that larger space of vector, larger space of inputs, your 422 would change. But the neural net is trying to learn, the thing that it learns may be something like this, that if in those 422 ones there was a not and there was a horrible, both were there, then it learns something different, whereas
So now it's 423 instead of 422, because it has not as one, horrible as one, and not horrible as one. So my input just went from 422 to 423.
no,
No?
because you did not do anything manually. Try to see
Well,
it in
no,
this way.
I'm just thinking.
Right. Yeah. So if that, yeah. So then the intuition is correct that you had a certain number of inputs, but you could learn many relations between those inputs, and that's why your space can
Okay, and it's the relations that make you have a larger.
large.
Then you want
That makes
all the bigrams to be squared.
Right.
Right?
Right.
But we
That
may
makes
not care about all the bigrams.
Right.
You may not actually use that big, but this is why we come up with it.
That makes sense.
So
Okay.
given a certain size of input, you can always expand. I mean, you want to learn more and more features. So at some point, you are going into bigger layers. The idea is not to funnel down to a final conclusion. That's only if every piece of information you wanted was contained within the input. But how can we assume that is true?
Right.
In this case, it's absolutely not true. So you want to learn whatever you can.
That makes sense.
So this is one example. I mean, we can just build it here. Why worry about that? 1000. That's a model. So we just have a large model with 1000 in the middle. So now one of the layers got really expanded. So in a block diagram, we don't see the change. But if it were in terms of neurons, it's a really large layer in the middle. And we may be able to learn that very well. In fact, I mean, for this case, I would recommend starting with the larger number anyway. 128, 64 were like, that's just, it's easy to deal with 2 to the, like powers of 2. It's very intuitive. You just deal with those writing
How many
numbers.
data inputs do we have?
We have 422. Oh, how many total data inputs?
Yeah.
In reality, we have a really large number. I mean, I'm doing a sample
Wait,
of
how many,
100.
what they were, messages or whatever, but in reality, you want.
Yeah, so if I remove,
Okay. So if you have 100, then sticking 1,000
yeah,
nodes in the middle.
let's see this. So if I read the entire data set, then how many do I have? We have this many values.
Okay, okay.
So we have
You can
1595.
still have a layer with more neurons than. Oh,
Yeah, can I put 200,000 in my layer in the middle?
200,000?
Whoa. I think something bigger.
Yeah,
than
now,
100.
so you have to
I
remain
mean, I
in
guess
certain,
you can't, because you just put 1,000.
Yeah.
You only have 100.
putting in the number you
No,
can.
so the answer is you can definitely do it. Now, will it train?
Yeah, most definitely not. 200,000.
Apologies if my questions are all stupid. You can make me stop anytime. Whatever it is.
No,
Don't get it.
there are no stupid questions where I'm sitting.
Okay, we have this up till here. So now defining the model, developing model, that phase is clear.
Yeah.
Now
Not
next,
how we pick the magic numbers, but
so that's the process of hyperparameter tuning, which is a long process all the time. But we start with something which seems reasonable. We like, let's say your hyperparameter space is like this. You start, it's like it's going this way. So you, like 100 parameters, 2000 parameters, right? You start with a value over here, your results are horrible, you try a value very close to 1000, and you're sort of trying to boil down to some reasonable values by trying the extremes in both directions.
How much time, and this is probably another stupid question, how much time do you spend sort of looking at the data to get a feel for it before you guesstimate these 128, 64s, zeros? Do you spend any, because I mean, you deal with massive amounts of data.
Yes, the process goes in. I mean, you have to spend more time with it, and just by looking at data, maybe you won't get anything. So you have to follow this kind of process. Try extreme numbers and see how bad are the results. Like, is it learning anything at all? And if you reduce it down, is the performance similar? So where to find first you choose your first layer, right? How much to expand to, or how much to just boil down to the first layer. Then you are sort of doing a relative thing that, okay, layer after layer, maybe I can do one more of the same size layer, but then you're ultimately reducing down to the final space. But initially you have to expand. You mostly have to expand because there is not enough information in the data going here.
Am I right in looking at, if I did put in 1,000, I'm telling it that with a vector of 422, I want the computer to find my original 422, and then I want them to find 578 connections between the 422 to expand it out to 1,000.
no, you know, the 1,000 doesn't necessarily contain the original 422.
Oh, it doesn't even.
Yeah, because
Right,
it's
completely
sigmoid of
connected.
WX plus B, right? You take them individually and you perform an operation on them, and your layer is taking all of them. Like, it's a fully connected layer. So these are also called fully connected neural networks because all the values of a previous layer are going into calculating the next value at a node.
What if it can't? Like, what if I had a vector of 4 and I said, okay, 1,000, I want you to come out with an output of 1,000. Would it just go, seriously?
And if you have enough data, it would just learn a lot of them to be 0, and it would just learn reasonable valuable ones. I mean, so if you visualize your layer that it ends up learning in the middle, most definitely a large number of those will be 0, 0, 0, like because it didn't need any more information. It could find some values, and then everything else probably got down to 0 or got down to a random value within a certain distribution, which was not usable. But if you have a lot of data and your model is slightly bigger than what you needed, it will end up learning something reasonable. It will learn how to ignore certain extra pieces of information that you're sending it. Okay, let's move to training and optimization, which is that now you have a model, but the model has not dealt with the data yet. It's just a model sitting in somewhere. How do you train it? How do you update these weights? How do you reach to the set of weights which give you the best value? That's the process of training and optimization. So you need a criteria and an optimization method. The two things mean, if you remember the cycle, you do a forward pass, right? You take the data in to the model, calculate something. Now that value, the prediction value with the known truth, is used to calculate the loss, right? that loss will drive your optimization. How do you optimize, right? And then you have, so I mean, that's the criteria behind your optimization, that this loss is the point of concern that I'll use. But what is the algorithm that you're using to update those values? In neural nets, they generally follow into the family of gradient descent based algorithms. Now, that's in itself is a large space, but what we are doing is we are doing a process called backpropagation. You went through the neural network to derive a value. At that particular value, you could derive the loss. How much far were you from the real value? Now, using that loss, you go on updating each and every weight. And you follow a process called gradient descent, which means that if you have a function which is a convex function, right? It looks something like this. And let's say you are somewhere here. If you move along the direction of the tangent, means if you move along the gradient, if you're differentiating, you are deriving this gradient, you can reach the minimum, right? So you continue going down and you reach here, and then you reach here, and then you reach here, over here, and you keep going. Basically, you have reached the minimum. Your slope will reduce down to 0 if you have reached the minimum. So that's the process of gradient descent, which is the gradient descent algorithm in maths. Backpropagation does that with respect to your final output. You do it first with the loss. You can update one layer, right? Now that layer could be obtained as a function of everything underneath it. So you derive the corresponding gradient for each of those because you know the chain rule of differentiation, and then you pass those gradients downwards, and going through the process till the base, you have your del loss, like basically final loss by del x, which is the gradient corresponding to the input. That's the thing that you get at the base. So throughout this process, you are sort of performing the gradient descent using backpropagation.
So when you're optimizing the loss like that, if your step size goes beyond 0, how do you stop?
Yeah, that's where something called, that's another hyperparameter. Remember I said learning rate in one of my hyperparameters, which is, so that rate is taking care of how much really I move down. So this can always happen that I just go over here and then I start to go up. And that's basically that's not taking good enough care while doing the training. So you have to control a hyperparameter. General practice in really large models is that you start with a large learning rate, that you are taking sort of larger steps, and then after certain steps, you reduce the learning rate to a smaller size. And most of these things are done with heuristics and manual approaches that after 100 epochs, reduce it by 10, like divided by 10, divided by 10. And then the updates that you're making go smaller and smaller because you want to reach to a minima and not cross it. So exactly, that's a good point. Yeah. So in Keras, if you want to use these things, you have Keras.optimizers, which gives you different optimizers. So SGD is the main one, like the basic ones, stochastic gradient descent. But now there are many variants. So stochastic gradient descent sort of does this standard x minus learning rate times the gradient. Whereas you can use many smarter algorithms. So when you build complex models, there are options like optimizers. There's something called Adam, or these are examples: Ada Delta, Ada Grad, Adam, Ada Max, and there are RMS Prop. Like there are many algorithms, and they have their different properties. They were developed over different points in time. But for now, let's just stick to SGD. Yeah. So there's no good answer. I would say if you have a large model, try with Adam. Works really well. It takes care of two particular things. Like in the definition, you're going down like 2 stages. So let's say you're taking care of the mean as well as the standard deviation while moving down. So Adam works really well. RMS Prop works really well. But there's no fixed definition. I mean, I've seen cases where Ada Delta just works out to be the best. But more or less, I have had really good results with Adam.
in the current standard, it's the user has to pick all these hyperparameters.
Yeah.
Because they just seem like more things to constrain.
Yeah, and
So I
then
feel like I should always say, I have no idea. But I'll come back in a week, we figure it out. Right? And it just tries all the
It'll
whatever
try everything.
parameters, but like, no, that's not the standard. The standard is I spend my week to figure it out.
yeah, or more or less just look at the algorithm that the best algorithm in that space used, and maybe that's a better approach. I mean, for a starting point, that helps. And that's what I'm saying, like Adam more or less will give you a really good result, but there's no theorem that can prove that it will give you the best result. There's no real way. I mean, yeah, it depends on the data, it depends on the problem, it depends on the choice of network architecture. In several cases, like the learning rate can never really be high. I mean, you have to move very slowly, and maybe you cannot find the minima easily. So depending on the underlying distribution of the data, these things vary extensively. But you have the loss, you have the optimizer. So optimizer defines the method that you'll be following. This is pretty interesting. The SGD would just do sort of this. And now using the two, you will, at every step, you will do this, right? And then you select how many number of iterations you need. So that curve of forward pass, predict value, loss, and then update, that just keeps on going on. Model.compile is an operation in Keras, which means you have a certain model which was just defined, not compiled, so it has not converted itself into a graph to be placed on top of TensorFlow. We compile that, and it now knows what it will do. So the time when you want to run it, it's available. So that's just an operation of the library that you need to do. And at that stage, you are telling it what is the optimizer it should use, what is the loss that will drive that optimization process, and what are the metrics that you want. So let's say I want, in metrics is always a list. So let's say I want the accuracy at every step. I can do that. So now when you're compiling your model, you are giving the three things. What is the optimizer to be used? What is the loss? There can be multiple losses because you can have multiple outputs from your model. Our model looks very simple. It's just, this is the output, that's it, right? It's very straightforward. But I can have a model where there's another output here, there's maybe another output over here. You can build really complex models, and I'll go over those later on, like how, why they are important at times. But this thing can have multiple values. There can be different metrics that you want to calculate. Metrics are not required. Optimizing losses is always required because that's how you train your model, right? And now you train. So let me remove the metric because it's blowing up the visual. Okay. So fit is the term used for fit training. I think it's more because scikit-learn, the first famous library in Python, used this nomenclature, fit and transform. Fit is when you are training your model on data. Transform is when you're just predicting on top of it. So that's a nomenclature which scikit-learn used. And Keras also uses the term called fit, which just basically means perform the training cycle, perform that complete cycle. And it takes input as input X, what are the inputs, Y, what are the targets, right? So this is real data. Finally, this is a step where I'm merging my model with the data. Up till now, the models had no touch with the data. It was a separate model and it knew what is the shape and everything. But now finally, this data is running through the model, updating it at each step. And epochs is the number of iterations that I want to run it with. So I can, let's say, have just 10 epochs. And then validation data is what it will validate on after each epoch, right? So at each step, it'll do this. So now, over here, what it is that after first step, I had a loss of 0.39, which was fine, and the validation loss was actually lower than that, which is good. You want to reduce the loss. This might not be a good representation because we have 100 samples, but what you're trying to do with val loss over here is that once it sort of stabilizes, you are in a position that, okay, my validation loss is not changing much, So let me stop the training process now and then evaluate.
What's the loss?
Loss over here is a certain kind of loss which is called categorical cross entropy. But loss,
But that's on the training data.
it's on both data because validation data also has the targets. On training data, this loss is being used to update the model. This loss is not being used to update the model.
The model is updating only on the training
Training.
data. The validation data is only so you're getting a number so you can tell what's going on.
Yeah, so you can tell whether it's learning on the unseen, whether it's generalizing or not. Because see, this is going down because we are doing that process to take it down, make
Should
it.
by definition.
Yeah,
Right, unless it's
this has to
training
keep on
against-
going down. But is it affecting the validation loss as well? I mean, in this
So the
case,
validation loss could go up if I
Yeah.
made it
yeah,
inappropriate.
yeah, exactly.
And if it did go up, then you would be, what, overfitting to your training data? Is that right?
If
That's why
if your
you're-
training loss is really low and your validation loss went high, right? Then
Well,
you're
no, I mean, if on one iteration, your value loss is lower than on the next iteration,
Mhm.
but your training loss is going down,
Mhm.
but your value loss is going up, it means you're overfitting to that particular data.
That's
right?
very much possible. I mean, at the beginning, this can happen, and then it's just a random chance because you really haven't learned anything. So maybe on the validation sample, it gave a better result. But if it continues to be the trend, right? If your validation loss keeps going up, you're overfitting. And that's why you want to keep a check on validation loss and the process of early stopping, which means that's a process to control the hyperparameter space that while the model is doing this training, do stop the training, do like, let's say I set it up for 200 epochs, but after 40 epochs, my validation loss starts to go up. So an early stopping is a callback in Keras, and it's a method basically with which we will say, okay, we could go up to 200, but we are stopping now because our validation loss is going up. So there are methods to do that. But this fit is the train cycle running for a certain number of epochs. One thing which is happening now is that because I compiled the model here and I haven't recompiled it, if I run this again, I'm actually running it beyond those. So I'm not starting from zero. I've ran for 10 epochs, and because I haven't compiled again, this model.fit is going to run it more. So it's not starting from a fresh state of the model. Whereas when you compile the model, it creates a fresh state. After continuous fits, you're basically just
With the first state, you mean like essentially all the internal numbers are zero.
random.
Or whatever
Like they are set to the initializer that was defined. So it's not
Okay.
zero mostly. It's like there's an algorithm called GlowRot, which is used
Okay,
to
there's
do.
some way to
Yeah,
adjust, so
but-
like whatever is going to be our starting, but then after you run it, it just keeps whatever was the internal state.
because it's updating the same model, right? So this optimizer criteria, compile and fit. That's the simplest way to just train like a basic model, which is in your linear regression or regression neural network space. And the model definition can keep on being more and more complex, but this process would still remain the same. I mean, you might have multiple criteria for multiple losses, but the overall thing would be that you will compile and you will fit the model. Up till this point, are there any questions? Okay, so now the final step is to evaluate. What evaluate is doing is that you're sending this, now you're not updating the model. You're using whatever the model is, passing the test data through it, and it had its own targets, and you're calculating the loss. And the loss came out to be really high. So we did a really bad job at training the model.
Well, actually, it'd be any different than the validation. Because we don't use the validation at all when we're training either. We're just looking at that number.
Yeah,
Right? So why would the test be worse than the validation? The random sample is drawn from the same distribution.
yeah, but this particular random sample basically shows a really bad result in this case. I mean, the difference between this and this is actually really high. And I don't have a good answer for that, but that might just be the case because like we have a really small data set.
Rather than the,
20 over 20 iterations.
Right.
So not 20 over 20 iteration, no, 20, there were 20 samples in our test data set. So the number of samples. Because if you have a larger test data set, then maybe you cannot send that all at once as well. So that's why it does something. I mean, if I have.
So how many times how many like iterations are there?
So you can say there were 10 when we were training, but I did it like multiple times. So there were technically more than 10.
Okay.
But if
But for testing. Or
for
just once?
testing, why would there be an iteration, right? You are not updating anything.
I guess just to see if the output value changes.
Yeah, well, at this point, it's a mathematical formula with a deterministic output. You have a certain number of values, and there's a certain formula of calculation, Wx plus P sigmoid on top of it.
Mhm.
If those values don't change, nothing can change. If multiple efforts on my test set give a change, there's something wrong. Right? So in test, you basically do it once because that's the value. Basically, you just had a trained model. And now, well, a trained model is like a black box function. It will give you one value.
Mhm.
And model.predict does similar thing, but it doesn't do the comparison with the test target. So this is what you will use to visualize, first of all, the results. And secondly, to just see how your model, I mean, when you don't have labels on your data, when you're putting it in the final practice, you have a model which works, right? And now you don't have any label, you just want to give the result of a training model. That's when you use model.predict.
So evaluate is essentially predict and then these squares or something versus the corruption.
Yeah.
Okay.
So target is the ground truth, calculate the loss. The loss that was being used to update with the same formula, calculate the loss, but don't update. That's evaluate. And you want it to be really low or close to whatever your training loss was. Whereas we don't have that close at all. Okay, that's the complete process. Now we don't have much time. Let me go over projects quickly. So next Tuesday, so this is just what we wanted to cover in the project space, which means they have to be in small groups, given this class size. I mean, I would say 2 is a fair size, or if you have a group of 3, that's fine, but 2 is a reasonable number, because then we'll just have 6, 7 projects. But it has to be a working prototype of an ML-based solution, right? So this was the pipeline, the larger picture that we described. It has to be identification. What have we covered around identification? Went over the UN global goals, went over AI use cases that can be mapped, and we had a mapping of those. So that's a part to understand the broader space of societal challenges and AI being applied to it. And then definition can come from the example. So in the McKinsey reading, when they have discussed the AI use cases, they have given certain examples. That's where you define your ML solution. So you can look at that, and then you can look at real world situations. You can look at data sets to see what is the definition, but it will give you a problem to solve. And now with the solution, you have the ML pipeline, this pipeline that we have discussed, right? So now, since you have the problem, you build up to the stage and you evaluate. But one thing which we haven't covered so far, which will be covered later in the model, is deployment. That given a solution, given a model that works, how do you deliver it to the final stage? For the purpose of this class, solution is the most important space, and because you want to know how to build this, right? Identification is something which the experts of the domains will do. Definition is something which you will do in interaction with them. Let's say it's a real world situation, and you have some experts from UN coming in, and you're the ML expert for them. You will interact with them. They will explain to you the problem. They have identified certain situations, and they're creating, we want to solve this particular thing. This is the information that we have. Can you create a defined problem for your ML solution? And then the solution part is completely your job, which is the pipeline that we discussed. Build the entire process, build solutions, keep on evaluating. You have data sets, you keep on evaluating on those, and now you have a final thing. You want to use that model.predict, right? The point when you don't have the result, you don't have any label, you really just want to deploy the thing, and that's where you reach deployment. So the way I'm dealing with why I said model.predict is that consider that you built an entire model in Keras and now it's running on a server, and your final job is on a website. That website is calling the server. The only thing it really cares about at that point is that the website is responsible for getting your input data. It will take that data back to the server. You might do some pre-processing, whatever is required. Everything happens either at the client or the server. You have a trained model sitting somewhere in the server. And you finally run model.predict. You cannot run model.fit or like you're not training at every iteration, at every input. You are just using that trained model, doing the prediction, getting that value back to your client, back to the website maybe, and returning it to the user in whatever way you want to. If it's a classification and you derive the value of a certain class, then maybe the result that you want to give to the user is the text associated with that class and what is the real world output. But that deployment portion is important in any real application. So we will take care of that later on. But up to here, we have discussed. So start thinking of projects along this process. Think of an idea, think of a space, try to find different data sets. So remind me to, so I will put up links to different dataset repositories. If I don't do that by tomorrow, please someone post on Piazza that you don't see the list of datasets and then I do that. But I have some, I've found like a large number of datasets. I can link you to those, but if you have access to anything in particular, if you know from any use case, it's a good dataset, try to find them and try to think along the projects on this pipeline. And these will be the requirements to, at the end. But before, I mean, you get started, are there questions around the project?
So you will suggest some data sets for us to.
Yes.
Short paper in sort of a conference format or just like
Sure, yeah.
with like abstract intro,
Exactly.
completed works?
Yeah, so it's going to be a practice to write a paper for an applied ML space, how those papers can be written.
Or would it be more like the Google blog posts that we've seen?
No, it would be more like an academic paper. Okay, so I'll put up the list of data sets, but keep finding data sets, keep thinking about the problems, and next Thursday in the class, you have to submit by then like a title and a proposal for the project, and we'll go over it in the first 15 minutes because it's a small class, so we can go over most of them. And I've created Slack, and I think now we have the enrollment closes this week. So by the end of this week, we'll definitely have the final list of students, but I'll put everyone in Slack. That's where you can start creating your teams if you have decided on the team already. But each team can be a channel on Slack.
You say everyone, next Thursday.
Next Thursday.
Thursday the 25th.
This Thursday.
9 days from now.
9 days from now.
Yeah, okay.
Is there also an assignment?
That will be due for, it will be due next week because now it will contain neural nets.
It'll be due the 26th.
It will be due on 26th. Assignment and reading on Piazza are due on 26th. Reading discussion next Tuesday, which should be a discussion where everyone should have read the papers and should have content to contribute in the discussion. Project proposal due also 26th. Make that 26th. Everything is due 26th. Yeah, it's gonna be easier that way. Everything is due on 26th.